Good morning, Math BH. You should have out lesson 7.2e, either the PDF electronically or printed, and we're going to match some graphs to stories. So number 1, Lucy walked away from her house at a steady rate. On each graph, the distance represents the distance from Lucy's house. So if she is walking away from her house, then we should be getting farther as time goes on. So we know the distance has to increase as time increases. So I like A. B, I don't like because it's going away from her house, but then it turns around and goes towards her house. We never said that we're going. C, I don't like because the distance is the same. So over time, she is standing still. She's away from her house and she's not moving. And this one, we're going towards her house because as distance goes on, our distance, as time goes on, our distance is getting closer and closer and closer to home. This would be walking to her house, not away from her house. So here we would have A. All right, number 2. Sunny walked towards the swimming pool at a steady rate. On each of the graphs, distance represents the distance from the swimming pool. So this time we don't want to go away from the swimming pool. We want to go towards the swimming pool. So I know I need a negative slope. So I'm liking D because it's a negative slope. Okay. Here, I'm not happy with the first one because this is going away. And this one is going away and then towards. And this one stays the same. The distance isn't changing. So I like D. Moving on. Anna ran towards the beach and then walked away. So here we're going to be changing slopes. We need 2 different directions. On the graph, the distance represents the distance from the beach. So when she's running towards the beach, she's getting closer. So we need to start out negative. And then when we walk away, we're getting farther away. So we have to start negative and then go positive. So C. Max stood still as the others were running. So Max's distance isn't changing. Over time, he's staying exactly in the same spot. So that would be C. Okay. Why are the graphs above graphed in first quadrant? Because we can't have negative time. And we also can't have negative distance. If we go in a different direction, we're not going negative. I don't say I go negative 20 miles to Mexico. I just say I'm going 20 miles. So here, both distance and time cannot be negative. All right, moving on to the next page. Use the distance time graph to answer the following questions. So now we're going to read the graph. What is the speed during the first 20 seconds? Okay, so I know that speed is equal to distance over time. So I think about that. Speed is equal to distance over time. So in the first 20 seconds, my time is 20 seconds, I haven't moved anything. The distance, the change in distance is nothing. So this is the change in time and this is the change in distance. Here I went from 0 seconds to 20 seconds. And here I stayed at 10. 10 minus 10. So in the first 20 seconds, the person did not move. Okay, B, starting at 0 seconds, what is the distance after 50 seconds? So here, at 0 seconds, we had 10. At 50 seconds, we had 30. It's not saying what the change in distance was. It just says what is the distance after 50 seconds. After 50 seconds, they have gone 30 meters. Okay, if they ask you for the change in distance would be 20, but they didn't ask you that. The change in distance would be 20. Okay, what is the speed from 60 to 80 seconds? So again, speed, we have to do change in distance over change in time. So here, my change in the distance, change in distance over change in time. From 60 to 80. Well, 60, the distance is 30. And at 80, the distance is 35. So 35 minus 30 is 5. And the time was 80 to 60, which is 20. That's not a great 60, which is 20. So this is 1/4. So they're going 1 meter every 4 seconds. If we want that as a unit rate, that's 0.25 meters every second. Okay, usually when we have speed, we do it per 1 unit. So we're looking for a unit rate. When was the object traveling the fastest? Okay, so we want to see the greatest change. So what I'm looking for is the largest slope or the most negative slope. So I have to kind of think about that. Here, when I'm looking at this slope triangle over here, I see that this is going over 10 and up 20. So this slope right here is about 2. What's going over here? This is going down 10, 20, 35. And it's going over 20. And net 35 divided by 20 does not have an absolute value of 2. So right here, I see it going the fastest. So between 20 and 30 seconds. It is going the fastest. It says explain. It has the steepest slope. Okay, next question. Draw a possible distance time graph for the story described below. Label your starting points, ending points, and parts of the graph that represent in the given story. So we have time, we have distance from home. Stacy walks at a constant rate from her house to the bus stop. Okay, so she's walking away from her house. So we have a positive slope going up. Doesn't really matter what kind of slope, just positive slope. Okay. She sees the bus coming, so she runs at a constant rate to catch it. Okay, that means she has to go a little bit faster. So this one was the first sentence. I'm going to underline it so we can tell in the graph where it was. And then, excuse me, my second sentence is when she's running, runs to get catched up. So we have to take her and go a little bit faster. She's like, oh no, gotta go, I gotta run. So it's a steeper slope. She gets to the bus stop, but misses the bus. That's not good. She didn't run fast enough. After a short rest. So what's happening on her distance when she's resting? She is standing still. So we have her standing still, short rest. Okay. So this is her short rest. She turns around and walks back home at a constant rate. It does not say if it's a fast rate or a slow rate. It's just a constant rate. So linearly, we are going home. I'm thinking that she's going to go a little slower because now, or maybe fast, I don't know. She's going a constant rate home. Okay. So what does the graph look like when she walks from her house to the bus stop? She's having a positive slope. Positive linear, positive slope. She is walking at a constant rate away from her house. So okay, what does it look like when Stacy walks home? It's a negative slope because she's going towards her house. So I'm going to go ahead and just copy this guy. Can I? I don't know. Let's see. Control copy. Oh, so sad. I want to copy it. Nope. Okay. Negative slope. She is walking at a constant rate towards her house. What happens to the line if Stacy runs? So if she's running, it's going to get steeper. So the slope gets steeper. What happens to the line when Stacy stands still? It becomes horizontal. It is horizontal. Okay, next one. Create a story that represents the graph. Cynthia is doing research on the hot coffee when it is served. At one coffee shop, the coffee was served at 180 degrees. Cynthia bought a coffee, then left it on the counter to cool. The temperature in the room is 70 degrees. The graph shows the temperature of the coffee as a function of time since it was served. Story, include a statement about the temperature. So I want you to go ahead and pause the video and go ahead and write a story and then go do number 9 too. Okay, and try number 10. So you're going to try 8, 9, 10. I'll make stories too, and then we can kind of compare our stories. So go ahead and pause the video. Okay, your stories might not be exactly like mine, but maybe similar. When the coffee is served is 100 degrees Fahrenheit, which is too hot to drink. As the coffee sits on the counter, it rapidly cools down until it gets closer to room temperature. The closer the coffee is to room temperature, the slower the coffee cools until it hits 70 degrees, which is the room temperature. A toy rocket is launched straight up in the air from the ground. Okay, so here the rocket takes off at time 0 with an initial velocity of 96 feet per second. However, gravity starts to take its toll. So gravity is pulling it down. It's trying to go up, but the gravity is pulling it down. Gravity is not winning until this point at which gravity takes over. So here, it takes its toll, slows down the rocket's speed until it overtakes the rocket 3 seconds and sends it flying towards the ground at an increasing rate until it crashes to the ground after a mere 6 seconds of flight. So after just 6 seconds, you are left with a broken toy. Here we're selling something. When a game is first released, games are being sold at a high rate. Everybody wants it. Everybody wants it. Now most people that want it have it. So here is just a slower rate because people are picking it up that just didn't get a chance to get it yet. As time goes on, less people need to still buy the game. So the rate of sales slows down. That should be sales. Next page. Okay, so here you're reading the story and trying to sketch the graph. So go ahead and pause the video and try and see if we have similar graphs. All right, Zach walks home from school. When the bell rings, Zach runs to his locker and grabs his books and starts walking home. So first, we're at school. We're running around school, so we haven't left school. So we are running around school. When he's about halfway home, he realizes he forgot his math books. Oops, that's him walking home. Then he goes, oh no, runs back to school. He's at school, running around, going to his locker. And then he sprints home, so we're taking off fast. Number 12, we can't start class until there are 5 people. So at 150, we have a dot, and then we have a dot at an increasing at this constant rate, but just per person. So it can't be connected because we can't have half of a person. And on 13, $5 per hour for $40. So here we go. So sorry, $5 per hour and a flat rate of $40 for 88 hours or more. So at 8 hours, we're just paying $40 no matter how much time. And before that, we have our slope. All right, the lesson's done. Go ahead and work on your homework.